Hey, what's up guys? My name is Cherno. Welcome back to my game engine series. So last time we took a look at refactoring everything, moving it from our application class into sandbox so that we could actually have it in our kind of game application rather than have all of this rendering code and all this interaction code in our actual just Hazel application as part of the API, because that's weird. So definitely check out that video if you haven't already. That's a fun little description of the last video. Anyway, today we're going to be talking about a problem that we had in the last episode. We didn't really see the problem, so I'll just highlight the problem by showing you guys again what's wrong. But basically what we're doing is we're actually interacting with our game using the arrow keys. We're moving the camera. However, that movement basically gets applied every time we render a new frame. Every time we update our app, we move our camera by, like, what was it? I think 0.1, right, units. Every time we actually, like, if the arrow key is pressed, and we run into an application update as part of our update loop, we move the camera 0.1 units. Now the problem with that is, who's to say how fast our application is being updated, right? It could be updated 60 times a second. It could be updated 20 times a second if like our frame rate is low and we're lagging. It could be updated 144 times a second if we're VSynced to a 144 Hertz monitor. Or it could be completely, like, VSync could be turned off, we could be uncapped, we could be running at 4,000 frames per second. Obviously, in that case, our camera is going to move, if we're running 4,000 frames per second and we're moving 0.1 units per frame, the camera is moving 0.1 units per frame, it's going to move 400 units in 1 second. Whereas if we're running 60 times per second and we move the camera 0.1 units every time, then it's going to be a lot less than that, right? It's only going to move like 6 units per second. There's a huge difference. 6 units, 400 units, crazy, right? What we want to do is make our camera move the same speed no matter what, right? We want to this is actually a different way of just saying that we want our movement to be time-based rather than like CPU frequency based, right? So we don't want it to move as fast as our computer's capable of doing, which is a lot of the times that's what we want. If we're doing some mathematical calculation, we don't want it to take 1 second to calculate. We want it to do it as fast as possible. But with this, we actually want this thing to just take a second, right? Or to take like half a second, 1.5 seconds, however long that's supposed to go for. That's super important. And the way that we're going to do that is by basically tying our movement into real world time. And we accomplish that by implementing something called a Timestep or delta time, essentially, in our engine. If you guys aren't supporting the series, patreon.com/thecherno is a great way to help support all this stuff. Huge thank you as always to all the patrons that made this series possible. If you go there and support the series, you'll get plenty of rewards, such as access to like little planning channel on Discord, and where you can ask me questions and other patrons questions and stuff like that. It really is a good time. You'll also get videos early and access to a Hazel development branch in which I've done all this stuff that I'm talking about today. Anyway, let's jump in and take a look at what this delta time thing is. And in fact, might just explain it first. That might help. So delta time, the reason it's called delta time, you might have heard of that, or it might be called a time step. Basically, the way this is going to work, the way that we're going to move the camera by a certain amount is going to be like fairly simple. All we're going to do is we're going to see how long the last frame took, right? So in other words, if we're running at 60 frames per second, then a frame is going to take 16 milliseconds. Right? So 16 milliseconds of real world time passes. If we're running, at 30 frames per second, then 33 milliseconds passes, right? Different units of time actually pass. So we're going to measure that. We're going to measure how long a frame takes. And then we're actually going to propagate that number, that duration, into all of our update functions. So we're going to basically have a parameter on our update function that is going to let us know how long that frame took. And then from that, what we can do is actually move our character or our camera in this case, a certain amount that is respective to that actual time. Now, the reason that works and the reason that's important is as follows, because you know what? I'm just going to draw a diagram because I'm getting sick of moving my hands. Okay, so delta time or time step or whatever. Let's talk about how all of this stuff works. So essentially, the reason that we want that number, right, from this delta time, from this measurement of how long a frame took, we could get a number such as, let's just say 16 milliseconds, right? But we'll actually do this in terms of seconds. So 0.016, right? That's our time for if we're running at 60 FPS. So I'll kind of write two possible values here. And for 30 FPS, no, I screwed that up. 30 FPS, we'll say that our delta time was 0.033 or something like that, right? So that's our kind of time values, right, in seconds. So that's what we'll be kind of pushing into our onUpdate function. Now, why are we doing that and how is it going to be used? Well, what we're actually going to do is take this time value of how much time has passed between our frames and multiply it with our movement velocity, our movement speed, right? So the reason that's done is because let's just say that the best way to show this is just an example. We have this cube, right? We have this square. It's moving this way at a certain speed, right? If we want it to move from the left side of the screen to the right side of the screen in exactly 1 second, right? How many times does it need to move? Well, if we're running at 60 frames per second, then clearly we need to perform 60 little movements, right, to get to here. Now, if we're running at 30 frames per second, we need to do half of that. We only have 30 frames to get from here to here, and that is how many frames we're able to render in 1 second of real world time. So what we need to do is obviously move twice as far every frame. Because instead of rendering like 1 frame here, 1 frame here, 1 frame here, we end up rendering, you know, the first frame here and then the next frame here, right? So we might only render this many frames, whereas if we're running at twice the frame rate, we have to render the frames in between as well. This obviously creates a smoother motion, and that's why monitors that are like 144 Hz, you can really tell the difference even if you just move the mouse button, because it's actually just rendering more frames. And if you look at an animation, it's rendering more frames in the animation, which means that everything's actually moving more often, right? Instead of this cube moving 4 times in a second, it might move 8 times in a second, right? And that's kind of what we see here. In fact, that's why you can also tell the difference between like 30 frames per second and 60 frames per second. It's a huge difference of smoothness, right? Because you're rendering way more frames. It's less choppy, it's more smooth. That's what we kind of want to do. So what we do is we say that our movement is, well, I don't know, let's just say 1 unit, right? We move 1 unit, right? We take that and we multiply it by our delta time, right? In this case, because it's just 1, if we multiply 1 by this, we get 0.016, which means that our cube or our object moves 0.016 units to the right in that frame. Whereas if we're running at 30 FPS, it moves 0.033 units in 1 frame. That's like double, right? So it moves twice as far. Why? Because it moves less often. And we obviously want to get from point A to point B in the same amount of real world time, which is 1 second. So that's how this whole thing works mathematically. It's a really simple concept. A lot of people avoid this and do some weird hacks to get around it. I think I used to actually also do something like that in the past, but anyway, it doesn't matter. The point is you should never kind of try and hack your way around this. It's super simple to get this timing logic to work. Some people also like to only run their onUpdate function at a certain restrictive frame rate. So for example, independent of your screen refresh rate or independent of VSync or independent of your uncapped frame rate, onUpdate runs 60 times per second. And that might give you, and because of that, you'll move like, you don't need to multiply anything by delta time. You can move a certain amount inside your onUpdate function. You can hard code it to be that 1 unit, for example, or 0.01 or 0.1 or whatever. You don't need to keep multiplying by delta time because you can predict how fast this will go. That's not a good way of doing things. The reason that's not a good way of doing things is because that's great if your application is able to hit 60, but what if your frame rate drops massively? What if you're on 10 frames per second for a little bit because everything's lagging? Well, guess what? The game's actually physically going to run slower, right? Which, again, might be what you want, but probably isn't, right? Especially if you're talking about rendering graphics. You don't want everything to run slower. What you want instead is to render less frames. Now, if you're suddenly at 10 FPS, right, because you're just doing 0.1 movement every second without delta time, then in 1 second, it's going to move a total of 1 unit. Whereas if you're multiplying by delta time, the amount that it'll move at 10 FPS in 1 second of real world time will be the same as in 60 FPS because it's just going to move in bigger jumps, if that makes sense, right? So for example, instead of this smoothness, you might just get 3 frames like that. But the point is the object still takes the same amount of time in real world time to move, and that's what you want, right? So if that happens and you're at 10 FPS, then this time value would be 0.1. right? And in other words, you multiply this by 0.1 and suddenly it's a much bigger jump than if you multiply by a smaller number. And your game ends up running the same speed if the frame rate is below VSync, right? And the only difference here is that you just render less frames, essentially. You don't actually take longer to do anything, which is usually what you want. Okay, so hopefully that makes sense. Now we can actually dive into the code and create this whole kind of delta time step thing. All right, so to do this, as I said, we basically need to pass into onUpdate, we need to pass in that delta time. So let's talk a little bit about how that's even gonna work in the first place. So this run loop, this is the while loop in which we need to measure how long this frame actually takes, right? So over here would be a good place to actually do that kind of calculation. Now, what I'm going to do is actually inside Hazel, I'm going to make a new folder called core. And this stuff is actually going to have like a lot of the core stuff that Hazel has. Because I don't know, this is getting a little bit flooded. Applications in here, layer stack, I don't know. I'm going to do a huge refactor, I think, soon because I don't like how messy this is becoming. But inside core, I'm going to just basically make a little header file called Timestep. And I called it Timestep. So that's fantastic. Timestep. Okay, and this is going to be a little bit of a helper class for us. Basically, we're going to make a class called Timestep. It's going to be, you can even make this a struct if you wanted to, honestly, it doesn't really matter, but I'll still make it a class. We're going to do Timestep float time, right? And then we'll basically hold time. And we'll set it to 0 by default. And actually, we don't need to set it to 0 by default. We can just have the constructor set it and we can have a default parameter. So we'll set time here, and then all we'll do is we'll have some basic functions for retrieving the time, right? You could do a whole bunch of stuff here, right? You could, for example, have like, you could override operator plus or plus equals or anything so that you can increment time step that way so that you can really just have a wrapper around a float, and we might do that. But for now, we'll just have get seconds, which is going to return time because our time's in seconds by default, and we'll have get milliseconds because that can be useful as well. And that's just going to return time times 1000, okay? You could store the time in milliseconds instead of seconds, and then you can just, multiply by 0.001 to get it into seconds. But I'm going to store it in seconds for now. So that's how it's going to look. And we might add some other functions if we need to. Just thinking about it, like subtracting might be useful and other mathematical operations might be useful, but this is basically what we have for now. Very, very basic time step class. So now what we're going to do is inside application, first of all, I'm going to go into Hazel and make sure that this, we can put it here, include Hazel core timestep is here. Inside our application class, I'm going to include that as well. So include Hazel core timestep. Then we're going to actually have a timestep here, right? So what we'll do is inside here, don't know why all of this is an error, probably just IntelliSense. What I'll do is, and I should have had a divider here, private. What I'll do is I'll actually just have timestep, okay? And this timestep, and again, it depends if you want to do it this way or if you don't want to do it this way, it's up to you. I'm also going to have a little float. Actually, I probably don't have to have a timestep here, really. No, I don't. All I need is something called last time, right? And last time, which I'll initialize to 0, is going to be the time that it took to render last frame. I might say last frame time, okay? So this over here is going to be updated every single frame. So we'll say time here. And then what we'll do here is actually retrieve the time from our platform. So lots of ways to do this. You could just use, Windows basically to get the right time by using something like query performance counter. That's a huge thing. We might actually do that in the future, but for now it's just going to be glfw get time. Okay. Now that does mean that we tie this application class to glfw. This is kind of temporary because I don't want to make this video forever, but this should be in platform. We should have a platform class that is kind of, Windows platform, Mac platform, whatever, iOS platform, Apple platform, whatever you want, right? All different platforms that are going to have their own implementations, right? But platform getTime should be a platform independent way of actually getting the time. And for Windows, it would use glfw getTime. But I don't really want to set up the platform just yet because it's a bit early to do that. We could do it, but you know, we're not going to today. You can do that yourself if you want for homework, and we'll actually get around to doing it when we have more things to add into platform than just timing. So time is going to be glfw getTime, which returns time in seconds. So I'm just going to cast that to a float, right? And then we're going to calculate delta time. So we'll say timestep equals time minus m last frame time, right? And of course we can just assign it to a float like that because we have a constructor that takes in a float, so it'll be an implicit cast. That is our delta time. That's our time step, right? That's going to be how long this frame, like what the current time is, versus the last frame time. So we record the last frame time, we do our whole frame, then when we wrap around and get back up to here, we get the current time again, and we calculate the difference, or the delta. And that is how we get our delta time. And then we go into layer on update, we take in a time step, I'll call it TS. Now, you can see that I'm not passing this by const reference or anything like that. It doesn't need to be. It's just going to be copied because if you look at timestep, it is a single float, right? It is just a float. It's the same as passing a float, right? And over here, when we actually created every frame, we're creating that object on the stack. It's literally the same as creating a float. So I don't know, some people might be like, oh, you're creating a class for this. Why are you doing that? Why not just have a float? It's the same, right? It's basically a float with just some helper functions to make it more readable. Now, if you were using Java, I wouldn't do it this way because if you create a new object in Java, you're creating it on the heap, and that is a whole different board game. Or in C#, right? Although in C# you can use a struct, and that will be something on the stack. But anyway, the idea is that this is like totally fine, but some people might be a bit hesitant, but that's what it is, right? So we have our time step, we pass that into our layer stack. And then if we go to sandbox, you'll see that because we've enforced layers to have time steps now, we have to go into on update and actually make sure that we have our Hazel time step, TS. Okay, now let's take a look at if this even worked. So we'll say hz, what is it? hz info or something like that. Let's just say hz trace. So we'll say delta time 0, and then TS get seconds, right? So this should give us how many seconds it took. And then we might actually say, seconds, and then in brackets, I might put how many milliseconds it is just to test out everything. Make sure that we have both things working. Let's hit F5. See what happens. Obviously the first time around, it's not going to be 100% accurate just because for the first frame, we don't actually have anything recorded yet. We also get a bunch of compile errors. So this needs to be, we need to include this. So include Hazel core time step. Let's try and run that again. Because last frame time by default is set to 0, right? So when we do time minus last frame time, it's going to be the time since the last frame. There was no last frame. So it's going to be slightly inaccurate, but that's normal and that's totally fine. I wouldn't worry about it. Okay, if we look at this now, look at what we get. Let's stop this. So this is a 60 Hz monitor and VSync is enabled. So you can see that we get about 16.5, 6, 7, whatever, around 16.6 milliseconds per frame, or 0.016 seconds. Okay, so that's what we get here. That looks pretty good to me. Now let's use this inside our actual math stuff here, right? So when we actually do the camera movement, let's use this stuff. So the way we do that is you can just do m camera move speed times ts.getSeconds. Now what you could do is just add add a float operator to this so that you can cast it to a float implicitly, and then you can just do times ts like that. That's probably something that's worth doing, to be honest, because this API is okay, but I don't love it. So the way that we do that is we basically just say operator float, and then we can just say return m time, right? It's that simple, and of course you can mark it as const. What this does is it's used for a lot of things. You can cast things to bool. That's done very frequently as well, so that we can just if check something really easily. That's, for example, how shared pointers or unique pointers, you can actually check to see if they've got a value just by doing if and then the pointer, the smart pointer. In this case, we're just using float here. And what that says is you can basically use this as a float. It's basically like a static cast operator where you're actually just adding the ability to cast implicitly. Okay. Or to cast at all, really. So when you do try and cast to a float, whether explicitly or implicitly, it will just return time. That's what's going to happen, right? So you're adding like a cast operator, basically. So if we go back over here, what that means for us is that instead of using TS, we can basically do cool stuff like float time equals TS, right? Because we now have a way to convert TS into a float, and that is by using this float operator here. Now, again, it's useful. It's worth mentioning the fact that in this case, it's going to return seconds. If you want milliseconds, you have to ask for it. And in situations where you think it might matter if you're using seconds or milliseconds, it is much better to just use the actual function. But, since we're basically saying that in Hazel, by default, time steps are always going to be in seconds, and then milliseconds is the non-typical scenario, it's fine to just do this as long as you make it clear, obviously, in your documentation and in your code that this is going to give you seconds. Okay, cool. So now we get rid of this and we just have times TS and we have that everywhere, okay, for any kind of movement. And now all of this stuff is not tied to the speed of our game running. Now, what I want to do before I do that is show you guys what it was like before. So if I don't do that, let's see what the problem is. So obviously, if I run my code right now, I've got vsync turned on, which means that it's going to run at 60 times per second. And you can see that my delta time was 60 per second. In fact, I might go back to what we had before just so that we can see that. So if I just Control Z a whole bunch so that we get back to this, right? And I hit F5, you'll see that what we actually end up with is a time step of 0.16 seconds, right? So over here, 0.016 seconds, right? That's what we're at because vsync's turned on. Now let's go ahead and create a different story for ourselves. Oh, and one last thing that I actually wanted to show here is you can see how fast the movement and rotation is. It's that fast, right? So if we go into our application, and I don't remember if we created this API or not. Yeah, so we have set vsync, right? So if we go back to application when we create our window and actually set vsync to be false, right? What that's going to do is set the glfw swap interval to be 0, right? And it should run a lot faster, and we'll see our actual kind of real frame rate of how fast it's able to render frames, because now it's going to do it as fast as possible. And if we look at our time step, you can see it's a lot smaller. It's like 3 milliseconds, right? 0.003, okay? And I think it's probably using the Intel GPU or something like that. No, it's using NVIDIA. Okay, cool. So now if I try moving, whoa, look at that. That's suddenly so much faster, right? That's the problem that I'm talking about, right? We don't want this. We want it to be the same speed no matter if we have vsync on or off, right? So that's what we're trying to achieve here. So now if we multiply this with TS, right? So I'll just grab this and copy and paste it a bunch of times. And I'll get rid of this print thing. Now it's going to be multiplied by TS. So no matter how fast we run, we'll always run at the same speed. It won't be like super slow or super fast or anything. It'll be at the speed that we set it at. Now, right now it's going to be super slow because obviously our speed is quite slow, right? So we've said that we're moving like 0.1 units per second or whatever. That's really quite slow. So our camera move speed will change to be 1. And our camera rotation speed is 2. We might make that like 10 or something like that. Remember, this is in degrees. So think about how much you want it to rotate in 1 second. That's what this is coming down to. So we want it to rotate 10 degrees per second. Is that fine? Is moving 1 unit per second fine, right? Think about that. So I might say maybe like 30 degrees per second or something. I don't know. That might be too fast. 1 unit per second is probably going to be too slow as well, but we can see. So that rotation speed's actually quite slow feeling. So is the movement speed. Let's bump this up maybe to 5 and to 180. So maybe it takes us a second to rotate 180 degrees. That might be a little bit more reasonable. Okay, and you can see, yep, so that takes about a second, right? to rotate, and our movement speed is a lot faster. Okay, so that depends. Like this might be too fast for you, might not be, but the idea is that, you know, remember this speed, right? It's quite fast. Now what I can do is go back to application, make sure we're not doing VSync. So now VSync will be on, right? We're not setting it to false anymore. And now what we should get is, guess what? The same exact speed, even though we're running the update loop a lot less times now, right? Like a lot less frequently, because we're only doing it 60 times per second instead of like how many ever times we were doing it before. Okay, so you can see why time steps are important and how we can use them really easy. And we've created a really nice API for us that does everything for us. Again, could have just been a float, but this is a lot more powerful, and we'll probably expand this in the future when we want to do more advanced things with our time step. Anyway, I hope you guys enjoyed this video. If you did, you can hit the like button. You can also help support the series by going to patreon.com/the Cherno. Huge thank you, as always, to all the lovely patrons that make this series possible. Hope that was kind of informative about what delta time, what time steps are in game engines and in games in general. I think that it's a very, very simple topic that is often like glossed over. It's often kind of glossed over. It's often just like disregarded and just like, you know, whatever, let's just jam this in. It's not important. Or it's such a complicated, you know, we have to deal with timing. That's probably so complicated. There's maths involved. You know, let's just not do it. Whereas it's just so simple, right? And it's so simple, it's so powerful, it makes your game run properly on no matter what frame rate or refresh rate you're running on, right? If I now want to play this game of mine on a monitor that has like 120 hertz, 144 hertz, 240 hertz, it's actually going to render more frames properly. Like it's actually going to run properly, and you'll see that smooth effect. And all we had to do was just a little bit of maths and a little bit of timing logic, like 3 lines of just time. Right? Really easy stuff. That's kind of what I want this game engine series to be about, right? Just showing you guys how simple it is, how a lot of these things are so simple and easy to do. Now, in the next episode, I want to kind of talk about object transforms, because at the moment we have a camera that's fantastic, but what if I want to render like 3 different objects, 3 different like squares that we have here, or 3 different triangles at different positions on the screen? I can't actually do that at the moment, but I want to be able to do that. So we'll cover that next time, and then we might move on to more exciting things like just graphics related things, I think, again, because I mean, there's a lot of stuff to cover really, but I think, yeah, next time we're going to deal with object transforms and see how actually we tell our renderer where on the screen we want to render a particular object. Now, in the future, when we move to like an entity component system or some kind of like composable game objects or any kind of like system that actually deals with entities or game objects, they're going to have their own transform component, and then that's going to kind of feed into the renderer eventually. But for now, we're going to have a more simple system that just lets us arrange stuff. But anyway, we'll talk more about that in the next video. Thank you for watching. Goodbye.